In this video, we're going to look at the normal distribution. We're going to be able to recognize the normal probability distribution and apply it when it's appropriate. We're going to recognize the standard normal probability distribution and apply it appropriately. And then we're going to compare normal probabilities by converting to the standard normal distribution. So the normal distribution in general is bell-shaped. It's probably one of the more important distributions that we ever learn. Some of the places in which you see bell-shaped or normal distributions is in psychology and business, economics, the sciences, nursing, and of course mathematics. Some of your instructors in the past may be using normal, and currently maybe use a normal distribution to help determine your grade. Most IQ scores are normally distributed. Even real estate prices typically fit a normal distribution. And normal distribution is extremely important, but it cannot be applied to everything in the real world. In this chapter, we're going to look at the normal distribution, the standard normal distribution, and those type of applications that are associated with them. So a continuous random variable is considered normally distributed or has a normal probability distribution if its relative frequency histogram of the random variable has a shape of a normal curve. In other words, it's bell-shaped and it's symmetric. Let me just move this up. The normal distribution has two parameters that we're going to look at, or in other words, two numerical descriptive measures. The mean, which is mu, and the standard deviation, which is sigma. X is a quantity that is to be measured that has a normal distribution. So we'll say X is the random variable. It'll have a mean of mu and a standard deviation of sigma. So it's noted as the X being the random variable, the quantity that we're going to be measuring. And you'll see this little line that says, it's going to be distributed as. In this case, you'll see normal, this N for normal, and it'll have this mu, which is the mean, and this sigma, which is the standard deviation. Now, in general, when we are looking at symmetric data, the mean and the median are the same thing. And if you were to draw a vertical line through the mean, then you would have whatever happens on this side will happen on this side. So as an example, if I were to draw a vertical line on going through this, imagine, if you will, that is a perfectly vertical line and it cuts that perfectly in half, that then this side would equal this side. Since the area of the curve must equal 1, a change in the standard deviation sigma causes a change in the shape of the curve. The curve becomes fattier or skinnier depending on what you have for sigma. And change in mu, or the mean, causes the graph to shift to the left or the right. This means there are an infinite number of normal probability distributions. It all depends on where your mean, or mu, lies and what your sigma is. Now we know from previous chapters that what the z-score is the measurement, or how far away the piece of data that we're looking at, this random variable x, is away from the mean in terms of standard deviations. So what the z-score does is measure the number of standard deviations your number that you are interested in is from the mean. With a standard normal distribution, your mean will be 0 and your standard deviation should be 1. Otherwise, if you don't have a mean of 0 and you don't have a standard deviation of 1, you don't have a standard normal distribution. Now, when we are finding our z-score, since it measures the units away from the mean in terms of standard deviations, if the z-score is negative, then when we calculate it, that means that we are to the left of the mean. That means it is below the mean. It's less than the mean. If your z-score, when you calculate it, is positive, that means we're to the right of the mean. Then that also means that that value that we're interested in, the random variable x, is above the mean. So if I'm asked to find a z-score when x is equal to 1, this is the lowercase x. Now, this notation tells me that the random variable that I'm interested in is a normally distributed distribution. This is my mean for that distribution. This is my standard deviation, or sigma, for that standard deviation. And this lowercase x is what I'm actually interested in finding. I want to know where this lowercase x is in reference to this mean and this standard deviation. So the way in which I calculate that is I have my z-score is going to be my number, which is one that I'm interested in, minus 12 divided by 3. I get a value of a negative 3.67. That means that this number 1, which is in this normal distribution, is 3.67 standard deviations below the mean of 12. Negative means I'm below. And that's what I expect, right? Because if I have the number 1, it's obviously less than 12. And this tells me how many standard deviations I am away from the mean of 12. If we take a look at this example, we have for 2012, the SAT math test had a mean across the United States and everywhere else it was taken of 514 and a standard deviation of 117. The ACT math test is an alternative to the SAT and it's approximately normally distributed with a mean of 21 and a standard deviation of 53. If one person took the SAT math test and scored 700 and the second person took the ACT test and scored 30, who actually did better with respect to the test they took? The z-scores allow us to determine this kind of information if these are scaled differently, and they are. So first I'm going to do the z-score for the SAT. So I'm going to do z, and I'm going to do S for SAT. The number that we're interested in is 700. That's my lowercase x. I'm going to subtract off my mean, which is 514, and then I'm going to divide by my standard deviation, which was 117. My z-score for the SATs and that score of 700 is 1.59. This tells me that I'm above the mean, which I knew by just looking at the fact that 700 is larger than 514. But it also tells me I am 1.59 standard deviations away from the mean, and I'm above the mean. Now let's find the z-score for the ACT. So I'll do z sub a. So I'm going to do 30 because that was my lowercase x that I'm interested in. And then minus the mean, which was 21. And then I'm going to divide by the 5.3, which was the standard deviation. So again, the random variable, capital random variable that we are looking at is the score of a test. The lowercase variable x for the ACT is 30. The lowercase x for the SATs is 700. When I did this calculation, I ended up with 1.70. So this score is actually a better score than the SATs compared to the test they took, because this score is 1.7 standard deviations above the mean of the ACT test. So when we're looking at normal distributions, we can make decisions about what is better or worse if both things that we're looking at, or multiple things we're looking at, are normally distributed and they're scaled differently. Then we can actually make a comparison, because 700 looks like it's a good score in comparison to 514, where 30 doesn't seem to be that far away from 21. In reality, this was actually the better score. There are a couple of things that come with a normal curve. The curve has inflection points. This is a point where the graph changes curvature, and at one standard deviation from the mean is where this happens. The total area under the curve is always equal to 1, so this is true when we're looking at the normal distributions. The area under the curve to the left of the mean is equal to the area under the curve of the right to the mean, which equals 0.5. We talked about that as well, up above in my beautifully straight vertical line. The graph tails off towards the horizontal axis to the left and right, and we can use the empirical rule. What is the empirical rule? The empirical rule is x is a random variable and has a normal distribution with a mean mu and a standard deviation of sigma. Then 68% of the values, these random variable x's, these lowercase x's, these points of interest, lie between one standard deviation in each direction of the mean. 95% of these values that we're interested in are between two standard deviations of the mean. And 99.9% of these values of interest lie between three standard deviations of the mean, both below and above. Almost all the x values lie within three standard deviations of the mean. Here's the empirical rule. So when you're doing your homework, pay attention if it's asking you for the empirical rule or not. So the empirical rule is a good starting point, but if it doesn't tell you to find the probabilities or z-scores or anything like that, or the expectations, without telling you it's the empirical rule, you're going to use the normal distribution in your spreadsheets. Just wanted to say that. Now, this is what I was talking about. 68% will go between 2 standard deviations from the mean. 95 will go within 2, and 99.7 will go within 3. That means that the combination between this far tail and this tail right here, these two combined, must be 0.3% that's left out, right? So it's not very much. That means one side then is 0.15% is not part of the 99.7. So here's another way that you might see this. Say you're going to go 1 standard deviation above and 2 standard deviations between. How much would you expect? How much percent of the data would you expect to get? And so you can see you can add the 34, the 34, and the 13.5. And that will give you from 2 standard deviations down and 1 standard deviation up about how much that you would expect to get. Suppose X, which is the thing that we're interested in, not the individual piece, so it's capital, has a normal distribution with a mean of 25 and a standard deviation of 5. What values of X do 68% of the values lie? Well, if we are using the empirical rule, right? So we have 25 is my mean. If I add my standard deviation, which is 5, and if I have my mean, which is 25, and I subtract my standard deviation, that means to get 68%, which is 1 standard deviation down, 1 standard deviation up, that means I would expect between 20 and the numbers I'd be looking for, I would expect my numbers to lie between 20 and 30. So that would be the values for X that I would expect 68% of my data to lie between the number 20 and the number 30 for my values of X, the lowercase x. The number of potholes in any given 1 mile stretch of freeway pavement in Pennsylvania has a bell-shaped distribution. So that tells us it's normal. The fact that they're telling us a bell-shaped, that means it's normal. The distribution has a mean of 62 and a standard deviation of 5. Using the empirical rule, what is the appropriate percentage of a 1 mile long roadway with potholes numbering between 47 and 67? So the first thing I'm going to do is figure out 62 minus how many standard deviations is going to give me 47. So I know my standard deviation is 5. So if I take off 1 standard deviation, am I going to get 47? And the answer is yes. So 47 is 1 standard deviation from the mean. And then I'm going to do the same thing with 67 plus how many standard deviations get me, or excuse me, my 62, which is my mean. Go back to my mean. 62 plus what? How many standard deviations give me 67? Well, we know that that happens to just be 1 standard deviation, so that's going to just be 1. So to go from 47 to 67, that means we are going 1 standard deviation up and 1 standard deviation down, which is 68%. What is the approximate percentage of 1 mile long roadways with potholes? Well, approximately 68% of the 1 mile long roadways with potholes between 47 and 67. What percentage of 1 mile long roadways have more than 52 potholes? Okay, well, 62, right? So I take 62, I have to subtract off to figure out what I get to 52. And I can see what I would put there is 2 standard deviations. So 2 times my standard deviations will give me that. So if I look at this graph up here, I'm going to go down 2 standard deviations. What percentage long roadways with more than 52 potholes? That means if I look at my graph up here, my normal graph, I know that it should be 13.5 plus the 34.4 plus the 34.4. So let's do it this way. We know it's actually going to be easier to do 100 percent because we're going to be talking about percentage. And let's subtract off what I don't see. What I don't see is this first 2.35, and I don't see this other 1.1 or 0.15. So rather than do an addition, let's do 100% minus the 2.35 and that 0.15. So this will tell me, because I am 2 standard deviations below, and everything to the right of that is this. So this 62 is 2 standard deviations away, or excuse me, 52 is 2 standard deviations down below the mean. And that means it's all of this. And rather than adding up all of this, it's much easier to take 100 and subtract off those two numbers. And I get 97.5%. So what percentage of 1 mile long roadways with more than 52 potholes? Now, using the normal distribution, suppose that a random variable x, that's the thing that we're interested in measuring, is normally distributed with a mean of mu and a standard deviation of sigma. The area of the curve in any values of random variable represents either the proportion of the population with that character or the probability. So this represents proportion of the population being 1 mile long roadways that will have more than 52 potholes. So 97.7%, that's the proportion, 97.5% of the roadways will have 52 potholes. But it's also telling me that it's the probability as well. Well, that's because we can take percents and go to the decimal equivalent. So if I wanted to know the probability of my random variable x having more than 52 potholes, that is going to be 0.975. That tells us then that the probability of getting a roadway, which is our random variable x, in Pennsylvania that has more than 52 potholes and a 1 mile long roadway is 0.975. Probability, percent of the population that has that characteristic that we're looking at. When we are looking at probabilities, we have something called a critical value. This is a line on the graph that splits the graph into sections. The shaded area in the graph here indicates the area to the left of the x, which is the thing I'm looking at, the random variable x. This area is represented by the probability of p, the probability p of this random variable x being less than some point of interest in my normal distribution. Normal tables, computers, and calculators provide a calculated probability if we're doing a normal distribution. And in this case, x would be the critical value since it splits a graph into sections. So if I were to draw a graph of my roadway, and what does that the 52 holes? Well, we know that the 52 holes is right here. There's where the 52 holes are. We wanted what is the probability of having a roadway in Pennsylvania with more than 52 potholes. This is where we get cut. This is the critical value. And what we were searching for was this part of the area under the curve. Couple of things to look at. If I want the probability of x being larger than, then it's going to be equal to 1 minus the probability to the left. Why do we want to do this? Well, because most of what we are finding is the left, what's to the left of the point of interest. When we do our normal distribution in Excel, by default, we're going to be looking to the left. So if I want to know the probability to the right, then I do 1 minus to the left. If I want to know a probability between two points of interest, two values that I'm interested in my normal distribution, then I'm going to take the probability to the right, the rightmost number, and I would then subtract off the value for the leftmost number, because that would be overlap, and that will give me that probability of the in-between. So the probability is x is less than x sub 1, and simultaneously that x probability of my 1 normal of my random variable x is greater than this other one is to the left and to the right of those 2 points of interest. And just as a reminder, equality, whether it is less than or equal to or is strictly less than, is the same. Just like if it's greater than or equal to in normal distributions is the same because we are continuous distributions. So the steps to find a normal random variable. Draw a normal curve and shade the area corresponding to the proportional probability or percentile that you are interested in. You're going to use a table or technology. We're going to use technology. We're going to use Excel to find the z-score that corresponds to the shaded area. Then obtain the normal value from the formula that x is equal to the mean plus the z-score times my standard deviation sigma. So the z-score tells us how many standard deviations we are from the mean. A percentile tells us what percentage of observations fall below a certain value or above a certain value. Depends on what we're looking at. So sometimes we want to be able to convert from a z-score to a percentile and back again. It all depends on the question that you're being asked. We're going to be using in Excel the built-in functions. So the normal.s.distribution, this is the standard normal distribution. That means my mean is 0 and my standard deviation is 1. So I'll use the is if I know that my mean is 0 and my standard deviation is 1. And z is a z-score, so we've already calculated that. So we'll either be given the z-score or we'll calculate the z-score. And then we're going to either say true or false. True returns a cumulative distribution. False returns a probability distribution. We will typically use true to calculate percentiles, and this will give us their percentile as a decimal. We can also use the built-in Excel functions to convert percentile to a z-score. So suppose we are a standard normal distribution. Again, that means my mean is 0. My standard deviation is equal to 1. If I'm given the percentile and I want to know the z-score associated to it, I will use the norm.s.invert. This is the standard normal distribution inverting, which means I'll put in my probability, and that's usually my percentile, and then this will kick out my z-score. If I don't know whether or not it's a standard normal distribution, or it just tells me it's not, or it tells me my mean is something other than 1, then I'm going to use the normal distribution. With a normal distribution, I will need the piece of data I'm interested in. I will need the mean for that data set. I will need to have my standard deviation for that data set, and then I'll make a decision whether or not I have true or false. Cumulative returns the stuff to the left by default. False returns a probability distribution function. We will typically use true to calculate percentiles of what we are interested in. And if I want to find my z-score, then I'll do my norm.invert. This is when I don't have the mean equal to 0. I will enter my probability, which is a percentile as a decimal. I will need my mean, and I will need to know my standard deviation. So if I get out my Excel spreadsheet, find the percentile for a z-score for 1.3. Now we don't know the mean. Since we are not given the mean, then we are going to use the standard normal distribution. So what I would put in my Excel spreadsheet is the equal and the norm.s.dist, because I don't know what the mean is. It's not given to me, so I'm assuming it has to be a standard normal distribution. Now it says that I'm going to then put in my z-score. Well, my z-score is 1.3, and then I'm going to put in true. And what should come out is 0.9032. What does this mean? Well, the interpretation could be two things. It tells me that this z-score is a 90 percentile. It also tells me that the probability of getting a random variable that is 1.3 or less would be 0.9032. So this is, we can think of this as a probability. We can also think of this as a percentile. Find the score with a percentile of 48. So again, we're not given the mean, we're not given the standard deviation, so we're going to use the norm, the invert norm. So we use the norm dot s dot invert, and I put in 0.48. What kicks out is negative 0.05015. This is the data piece that has that z-score. So this is the z-score that's associated with it. I should say, let me back up. This is the z-score associated with some given data piece. And this tells me I am below the mean, and that makes sense because a 48% would be less than the mean. If the mean is 50, then we would expect 48%, the 48th percentile, to be less than the mean. Let's take a look at this example. A patient recovery time from a particular surgical procedure is normally distributed. Cool. That tells us we're going to use the norm.s or the norm.dist without the s. It has a mean of 53. Oh, okay. So then we know, because we're given a mean, and that mean is not 0, we're going to use the calculator that we are going to use in our Excel is going to be the norm.dist. And that's the one we're going to use. We have a mean of 53 days and a standard deviation of 2.1 days. What is the probability of spending more than 2 days in the recovery? Okay. So we want to know that what is the probability that we're going to spend more than 2 days? Here's where my mean is. My mean, I'm going to mark my mean right here. My mean is 5.3. So 2 is probably about here, right? So this is about 2. This is where x is equal to 2. And we want to know the probability of spending more than 2 days. So this is the area under the curve that I'm interested in finding. So when I put in the norm.dist, I'm going to put in the 2, because I have to put in the piece that I'm interested in. And then I'm going to put in my mean, which is 5.2. Then I need my standard, 5.3, excuse me. Then I need to put in my standard deviation, which is 2.1. And then I'm going to type in, before I close up parenthesis, I'm going to type in true. Now, when I do this, this is actually going to give me this part of the graph, this black shaded part. That is not what I want. So what I could do to fix that, because I really want this other blue shade, is I can do equal 1 minus the norm dot dist to 5.3, 2.1, and then true. Because every time I'm using the normal distribution, I am by default finding the area under the curve to the left of my data piece. And what I get is 0.941958. Okay, so this tells me what is the probability. Well, the probability, this is what I should have wrote, is a probability that my x is going to be greater than 2. So greater than 2 is what my notation should have been. So probability that my x is greater than 2 is this. So it's a pretty large probability. And we kind of expect that, right? So if we would have said, what's the probability of getting 5 days? I would expect it to be closer to 0.5 because 5.3 is the mean. And since I want to know everything to the right of 2, that's a huge chunk. So that makes sense. So now I'm asked for the percentile. What is the 90th percentile for recovery times? So I'm going to use my norm dot inv. So I want to undo this, like inverting, undoing. I'm going to put in my probability, which is 0.9. My mean is still the same. My mean is going to be 5.3, and my standard deviation is still 2.1. And what I get is 7.99 or 8 days. So if you spend 8 days in recovery, you're in the 90th percentile in terms of recovery time. About 8 days, and that kind of makes sense. If this is 5.3, you're in the 90th percentile, you're going to be way up here somewhere. So that makes sense that you're way up here. So again, my mean is 5.3, and I wanted to know where the 90th percentile is, and it looks like it's probably right about there. That's about what it is. Take a look at the next example. The length of time it takes to find a parking spot at 9 a.m. follows a normal distribution with a mean of 5 minutes. Oh, that means we're not a standard normal. That means my mean is not 0. So my mean is 5 minutes and my standard deviation is 2 minutes. So it's telling me my mu is equal to 5 and my sigma is equal to 2. Based upon the given information and numerically justified, would you be surprised if it took less than 1 minute to find a parking space? Okay, so I'm going to do the norm.dist. I'm going to put in 1 because that's what I'm really interested in. And what I'm looking for is the probability of my value being less than 1. So I'm going to do the norm.dist. I'm going to put in 5. I'm going to put in 2. I'm going to put in true. And what comes out in my spreadsheet is 0.02275. So that tells me that I have a 2.3% chance of spending less than 1 minute. So yeah, I'd be really surprised if that happened. So again, I want to draw where 5, this is my mean. Less than 1 minute is way down here. So you can see less than 1 minute. Yeah, highly unlikely. Find the probability that it takes at least 8 minutes. Okay, so again, I'm going to use my norm.dist. I'm going to use the probability of x is taken at least 8, so greater than or equal to 8. But remember, continuous random normal distributions do not care if it is less than or equal to or strictly less than. So the equality part isn't really all that important. So I'm going to use the 1 minus the norm.dist, because remember, when I'm using the norm.dist, it's always finding the area to the left, and I need the area to the right. I need to know how long is it going to take at least 8 minutes. So here's 5. At least 8 is like way up here, right? So here is 8. And I want that part. I'm going to have the 8, the 5, the 2, and then true. And what comes out of my spreadsheet is 0.066801. So the probability of it taking at least 8 minutes or 8 minutes or more is 0.06687. So that tells us that we have about a 7% chance of it taking at least 8 minutes or 8 minutes or more to find my parking spot. 70% of the time it takes more than how many minutes to find the parking spot? So 70% of the time. So we're given the percent, so I'm going to do the norm.invert. I'm going to put in 0.7, 5, and 2. And this gives me 6.048801. Doesn't seem right, does it? And it isn't. So the norm.invert, right? When I'm doing this, it's just going to tell me where this lies. 70%. So my percent that I put in was 70%, which is, if this is 50%, which is where my mean is, my 70% is here. And that doesn't make sense. It makes no sense in this. So what I didn't want to put in was the 70%, because I want to know 70% of the time it takes more than. Well, that would tell me I'm way up here. This is the 70 percentile, right? That would tell me this 6 tells me that 6.048801, that tells me actually that 70% or less of the time it's going to take me this long to get it. So that's 70% or less. That isn't what I want. What I want was below that, right? So to get the correct one, you have to pay attention to what it is that you really want, and it's really important to think about putting in the picture. What I wanted to know is the 0.3, because really what I want to know is 70%. 70% of the time it takes more than how many minutes? Well, 70% of the time, that means I really want this number way down here. I want all of this, not that smaller. So instead of putting in the 0.3 or 7, I'm going to put in the 0.3. And this tells me that 70% of the time, it's going to take me approximately at least 4 minutes to find a parking spot. Now, when you're doing chapter 6, you're probably going to want to have some sort of spreadsheet that looks like this. I like to label everything. X bar is the samples, or mu is the population, and we're talking about a mean. Now, right now we're using mu. S is for samples, sigma is for populations. This is standard deviation. Right now we're using mu and sigma. A is some single piece of data. B is some single piece of data where A is less than B, and N is the sample size. We don't need that right now. It will be coming. A z-score is the number of deviations from the mean. So this is going to be A minus the mean divided by the standard deviation and the probability given when finding a z-score or something else. So we're going to put in an A value. We're going to put in a B value. We're going to be given a mean. We're going to be given the standard deviation. I'll be able to find a z-score for A. I'd be able to find a z-score for B if that's what they're asking me to do. So what I did was I took my A value here. I subtracted off my mean, so it could be X bar later. Right now it actually should be mu, but it's my mean. And then I closed my parenthesis and I divided by my standard deviation. I did the same thing here. I want to know the probability of X being less than 1. So if I'm doing a standard normal distribution, I would do the norm.s. I'd use the z-score and I can hit true. So if I want to do it this way, what the z-score does is it brings down these numbers and puts it in a standard normal distribution. If I don't want to take the time to find the z-score, right? Say I don't care about that right now and I'm just not going to do it. Then here, what you're going to do is you're going to do the norm.dist. So to change that, you would do the norm.dist. And then you would put in where you'd grab whatever cell has your A value. You would grab the cell that has your mean. You'd grab the cell that has your standard deviation, and then you'd write true. So say you don't want to spend the time to find the z-score. I'd recommend you consider finding the z-score because it's going to be helpful later. Even if it's not required now, I would consider doing it. And then if you're using z-scores versus the raw data piece that you're interested in, then you use a normal dist. If you're using z-scores, you use the normal.s distribution, standard normal. If we want the value to the right, then we do 1 minus the cell above. If I want it equal to, this is where we put false, right? So whether you're doing the norm.s.dist, or like I said, if you're not using z-scores, you're using the normal.dist, this is where you'd say false, and you get 0. The probability that X is less than B. And then here's the important one, is if you want the probability between 2 points, you find the probability of X less than B minus the probability of X less than A. And what that is, let me just show you a quick little picture. So suppose here is where B is, and when you do the norm.s.dist, because you found the z-score, or if you are using the norm.dist and you're using the raw piece of the raw data piece, the mean and the standard deviation, then this is what you're getting when you say true. Now, then here's where A is, and when you say true on that, you're getting that. But what you want is the middle piece, and that's how come you have to subtract off that little bit of the A. And so that's what this does right here. So you would grab the cells that would have that. So I'd grab this cell, and I would subtract off of this cell. So again, you're either going to use the normal.s.dist if you're going to take the time to find the z-score. Not a bad idea. If you are not going to take the time to find the z-score, then you're going to use the norm.dist. So assuming that you know that you know that you're in a standard normal, then you're going to use the norm.s.invert. If you are given the mean, right? So you would only use this. You only use this part when mu is equal to 0 and sigma is equal to 1. If you are not given that information, instead you're given a mean, then you're going to still do the probability equals, and you're going to enter that value. And now you're going to find the z-score. And the way you're going to do that is you're going to do the norm dot invert. You're going to do your probability, whatever this cell is. So let's say it was that 0.3. It's also going to need to know what your mean is. So you'll come up here and grab that cell. So that's your mean. And you'll also need to grab your standard deviation. So that is your sigma. And then that will give you your z-score. What it does not give you is the a value. Say if you were chasing the a value. What we know the a value, so you'd need to add another row and you say a value is equal to. You would grab the z-score, you're going to multiply it by the standard deviation, and then you're going to add the mean. So you in this cell right here, you would do an equal symbol. So let me put that cell there, and let me put that cell there. You would do an equal symbol. You would grab this box, and it would go right here. And then you would multiply it by whatever your standard deviation is. So you'd go up to your standard deviation cell and grab that. So you would add that standard deviation cell, so sigma. And then you would add to it, I don't know why I have that there. You would add to it your mean. So you'd grab the cell that has your mean, and that would be your mu. And that would be what you'd use if you are not a standard normal distribution. So here's another thing that you should probably add to your spreadsheet for chapter 6. And that's it for this video.